Hi, nice to meet you all. Pretty excited to be here. This is my third AU. So my name is Nick. Like many of you in the audience, I once was an architect. I'm recovering now, and I spend most of my time programming. This talk is called Intuitive Robotics. In a way, it's kind of about tools and embodied knowledge. The idea being that we're really great at interacting with the world using our hands, so manually, but we're usually terrible at doing so with math or words. So tools like VR, which favor intuition, subtlety, embodied knowledge, are going to have a real impact on the way that we work with things in the real world. So anyways, let's get into it. So this is the lab. I've been with Autodesk's Applied Research Lab in San Francisco at Pier 9 for about 2 years. And our mission is sort of to look ahead 5, 10, 100 years out for combined speculative applied technologies and to try to find blind spots for the larger contingent of Autodesk. And we explore everything from robotics, AI, to generative design, and even storytelling devices like graphic novels. The big idea is that in an age where infinite computing is sort of the new baseline, our old model of pushing our wills through our fingertips isn't really going to work anymore. And until now, if you couldn't draw it, you couldn't really imagine it, let alone make it. So in the lab, we're investigating what lies beyond our traditional tools. I'm trying to show you some images of the lab so you get a sense for what I'm about to show you. One such exploration we had here at AU last year, and it was called SHRMP, which stands for Supervised High Rate Metal Printing. In as few words as possible, actually, like if you were here in the previous talk, you would have seen something very similar to this, but again, in as few words as possible, it's a closed-loop, self-correcting, 3D printing robot with enough sensors and intelligence to do a good job without much intervention on my part, or the team's part. What was most challenging, though, was actually getting inside and seeing what was going on, especially when things didn't go as expected. It's super hot work, it's bright white light, burning ultraviolet light, so you need substantial guarding if you're ever going to actually get inside and work with the machine. For the most part, we couldn't, so we had to add cameras, scanners, lots of other sensors and devices to actually see and do validation as we were making these objects. We also did furniture-sized objects like chairs and lamps and tables. So to get a practical sense for our process, what we did is we made a digital twin of the lab. You're going to hear this word probably a lot. But we decided to virtualize everything in the lab, including the robot, using the Revit model of the lab. So we got the doors and the windows and things like that. We even took photographs of the textures of the floor and the walls and things like that. So we'd have as hyper real as possible. So that when you go inside, you actually inhabit the same space as you would in the lab. In a way, you can sort of work remotely, like from home, and it's going to log in from anywhere, which is one of the major aspects that makes working in VR kind of special. And as we went through the documentation, we kind of rigged up a dimensionally and functionally equivalent robot to work with. This included things like geometry, the kinematics, our motion control algorithms, positional data, I/O states, etc. And we started with a basic selection mechanic using the Vive controllers. This is, again, in virtual reality right now that you're seeing this. We use a laser pointer to kind of do forward kinematics on the machine. What you're seeing is that green and yellow lit rings around the robot, basically defining or telling us how extended or close to the limits the machine is. And with that paradigm in mind, we also implemented a way of reaching out and directly manipulating the end effector, which is that tool, that welding tool on the end of the controller. This is inverse kinematics. So when you grab it, the robot will literally just follow you around and match the position and rotation of the controller. Something we noticed early on, though, is that the controller needs to kind of smooth out. Our hands are actually really kind of jittery. So to give the robot a sense of weight in VR is actually a pretty important thing. Like that kind of motion is actually really difficult to produce on the real machine. You'd probably kill the motors. So from that point, we set up a live connection to the real robot, from the real robot in the lab to the virtual robot. So when it was welding, we'd see it welding in VR, and we'd be able to do process monitoring and see how far it was just in the print. So right now you're seeing little virtual weld beads get deposited. And we can also observe without any risk of injuring ourselves or without disrupting the welding process, this event that's going on behind the screens. So it was really informative for us as the developers, the people that are not expert welders in any way, to see what was going on. So for the digital twin that we produced at AU, we had to rig up our new robots. We didn't have these in the lab, so we started working with them virtually first, and we built these kind of robot species agnostic asset classes that you could add any sort of details about the system that you wanted to. Really, this asset could be anything. It could be a tractor or an Arduino or something else, but the idea is that you have a mirror of the real thing, the real machine in your virtual space. And the first steps towards working on this project, we took those machines and kind of worked in the actual AU exhibit hall, working on the user interface and the experience of moving them around. We spent a lot of time trying to understand how motion scaling might work. So when you grab the robot with the VR controller, the closer you are, the finer the resolution it is. The further away you are, the kind of faster you can whip the robot around. And understanding what convergence really feels like to us. How we expect a position to be in the right place or having reached a goal was kind of a big deal because sometimes in virtual reality we don't have the same kind of depth perception or the same force feedback that you might have with interacting with things in the real world. We also spent a lot of time thinking about toolpath creation and inspection. So this is something that's really typical, obviously, in the way we work with robots anyways. So a lot of people just program their machines with code, and others use the teach pendant, which is a kind of cumbersome and challenging interface. Other people use simulators, but all of this is a lot more difficult to use than just your hand. If you want the robot to go somewhere, you should just be able to say, grab the machine and tell it to go there, or point there, or use gestures or words in the same way that we talk to one another. So you don't need to have technical knowledge of the robot at all to operate VR, and the movements will be much more direct and intuitive with respect to your motion and expectations. You obviously don't have to spend any time coding. The other thing is that we had to deal with simulated interactions with real-world objects using the physics engine. So we tried to deal with as robust an environment as possible with respect to collisions, picking things up and putting them down, IOs, grippers, things like that. And even understanding how, as a user, we interface with that sort of stuff. So when you see the glass in the screen go red, it's collided with something. And something that's kind of interesting is that we immediately kind of back away and say like, oh no, you can't actually push the glass through that, it'll break. That's our kind of like intuition kicking in here. But it's VR, and you can just push it through any object you want. You could walk through walls if you wanted to. So there's all sorts of like kind of odd, there's a little bit of odd dissonance between the virtual world and the real world, and we're kind of trying to understand how that impacts the way we drive these machines. The last thing specifically is doubling. And here you can see a ghosted representation of the robot, which corresponds with the real robot outside of VR. The idea here is that from virtual reality, we can send messages basically via internet protocols to the robot and have it move around based on the virtual representation, and then get that data back and see a representation of the real robot in VR moving around. The same is true for other objects like things that we can track. So if you brought trackers into VR attached to the window or attached to a person, you can see them moving around the virtual space. So this is more a mirroring than a copy of the real thing. It's two parts of the same thing, two representations of the same thing. So yeah, the idea is that this virtual object is less a copy than the real thing. And the biggest difference is that when one robot is accessible from anywhere in the world, the other is somewhere bolted to a floor. And we can have this live relationship between one person anywhere and the machine that isn't based on code really at all. It's based on the way our body expects things to work, the way that we expect our hands to interface with the world. So it's a really direct relationship. You should try it if you haven't done it yet. One of the great things about this tool set is that we can immediately apply it to other projects. This is one of our senior engineers, and he's hoping to implement a practical robotic animation for filmmaking. And if he wants the shot to feel more natural, he can pilot the robot himself. He can also be in VR with all of his virtual assets. He can see what the camera is seeing. So it kind of like closes the gap between the virtual world and the real world to a certain extent for film. And obviously capture the nuance and subtlety that we would like to imbue in our toolpath. So there's plenty of room for kind of less or more flexible path planning in robotics. Another project that used this tool set tried to teach a robot by demonstration. This meant using VR to capture the way that a human solves problems, using a neural network to learn from the input and to control the real robot. So the premise here is that it's easier for us to just do something than, again, to describe it with equations and numbers. And the goal here is simply to get a block onto a glowing target. This is Charlotte. She was one of our interns over the summer, and she spent hours and hours and hours trying to teach our robots how to do things. And afterwards, the results did things like this. So this is the robot using kind of like an unexpected way on its own, processing that neural network to drive this little block into that glowing space. This is not a human controlling it. This is the robot, solving the problem on its own based on all the training data that we put in. So it's kind of cool. The robot doesn't always go where we expect it to, and the next step would be to transfer this to the real robot and see how that transfers. This took lots of debugging and lots of testing, so this is a kind of a nicer video than most of the other ones. So all of this is an effort to narrow the gulf between the virtual and the real worlds.